So we have a sample problem for molarity. We have a solution is prepared by dissolving 42.23 grams of NH4Cl into enough water to make 500.0 ml of solution. So first, we must know our known and unknown properties. So we have our mass is given in here, 42.23 grams NH4Cl. We have our molar mass of NH4Cl is equal to 53.50 grams per mole. We have our volume solution also given in here. We have 500.0 ml, which is equivalent to or could be converted into 0.5 liters. So our unknown property is the molarity. So we have to calculate its molarity. So after that, we will have 42.23 grams of NH4Cl times 1 mole of NH4Cl over 53.50 grams NH4Cl. So we could just simply cancel gram of NH4Cl here and here, giving us 42.23 mole NH4Cl over 53.50. So calculating this, we will have 0.7893 moles of NH4Cl. So using the molarity formula, we will have molarity, or denoted as M, is equal to moles of solute over liters of solution, or equal to moles over liters. So we will have from the equation earlier 0.7893 mole NH4Cl over our liter, which is 500 ml. Converted into liters, we will have 0.500 liters. Calculating this, we will have 1.579 molarity, or M. So the molarity is 1.579 m, meaning that a liter of the solution would contain 1.579 mole NH4Cl. Four significant figures are appropriate. In a laboratory situation, a chemist must frequently prepare a given volume of solutions of a known molarity. The task is to calculate the mass of the solute that is necessary. The molarity equation can be rearranged to solve for moles, which can be converted into grams. So we have freezing point depression, denoting from the formula delta TF is equals to TF solvent minus TF solution is equals to KF times M. So where delta TF is the freezing point depression, while TF solution is the freezing point of the solution, TF solvent is the freezing point of solvent, KF is the freezing point depression constant, and M is the molarity. So you have here sample problem. 2.00 gram of some unknown compound reduces from freezing point of 75.00 grams of benzene from 5.53 to 4.90 degrees Celsius. So, what is the molar mass of the compound? So first, we must compute the molarity of the benzene solution, which will allow us to find the number of moles of solute dissolved. So we will have from this formula, we will derive M. So we will have M is equals to our delta TF over negative KF. Then substitute, we will have this equation here, which is 4.90 minus 5.53 degrees Celsius. So that is our TF solvent and our TF solution, this and this, over our negative KF. So we have negative 5.12 degree C over M. Then we will have negative 0.63 degrees Celsius over negative 5.12 degrees Celsius over m. Calculating this, we will have 0.123, cancel the Celsius, m. So, for amount solute, we will have the 0.07500 kg benzene multiply to this, we have 0.123 m over 1 kg of benzene. That will give us 0.00923 m solute. We can now find the molecular weight of the unknown compound. So we have, for molecular weight, we have the 2.00 grams unknown over our mole solute here, 0.00923 mole. This will equal to 216.80 grams per mole. So the freezing point depression is especially vital to aquatic life. Since saltwater will freeze at colder temperatures, organisms can survive in these bodies of water. So for Hess law, we have this problem. Calculate the enthalpy for 2C plus H2 product C2H2 when C2H2 plus 5 over 2 O2 yields 2CO2 plus H2O. Delta H is equals to negative 1299.5 kJ per mole. C plus O2 yields CO2. Delta H is equals to negative 393.5 kilojoules per mole. And lastly, H2 plus 1/2 of O2 yields H2O. Delta H is equals to negative 285.8 kilojoules per mole. So, first, manipulate this three equation here. So, they could add up to this. So, this equation here add up to this. First, we have to do is reverse this whole equation, this first whole equation. Second step is, since we have two C's here, and then we only have one C here, so we have to calculate here, multiply by this by 2, and always remember that whatever happens here, you have to do the same also in the other side. So you have to calculate this and multiply with this 2. So in this third equation, leave it by itself, or we could just ignore this because they are not even in the equation here. So they are probably going to be cancelled out later. So following the first equation, we have to reverse the whole equation so that the CH2 earlier on this side could be in this side also. So we will have 2CO2 plus H2O yields C2H2 plus 5 over 2 of O2. So remember, we have a negative we have a negative delta H. So since we reverse this equation, we have to also reverse it, having as a positive 1299.5 kilojoules per mole. And then, since we multiply the second equation by 2, then we will have 2C plus 2 O2s yields 2 CO2, which give us also negative 787 kilojoules per mole, since we multiplied these sides by 2 and we also multiply these sides by 2. Always remember when you always remember that when you do an operation from this side, you have to do the same to the delta H, or the enthalpy of the reaction. And then simply writing H2, the third equation, plus 1/2 O2 yields H2O. Then its delta H negative 285.8 kilojoules per mole. So we simply add. So since we have two CO2s from this side and two CO2s from this other side, we could just simply cancel that. And then as we can see, we also have H2O here and also an H2O in this side. So we could just simply cancel that out. And then we have an O2 here, 5/2. And then we have O2s here, two O2s from the left side. So simply when you add this, 2 plus 1/2 is equals to its LCD 2 multiplied by 2. 4 plus 1 is equals to 5/2. So they're just the same, so we could just simply cancel them all out. Leaving as 2C plus H2 yields C2H2. And then adding this all up, we will have the enthalpy 226.7 kilojoules per mole. So as we can see, we have retained this for this equation here and the equation here, giving us that we have done the correct way of the equation.